Now, can you see my screen? Okay, thank you. At least one student told that. Okay, fine. So let's go ahead. So in last class, what we did, we basically in detail we read about the potentiometer, which is used for measurement of displacement, and we discuss about different types of potentiometer. Its different construction, like it could be like straight line, linear, it could be rotational, it could be helical type. So the several types of potentiometer we discuss. Then we discuss about the potentiometer input output relationship, when it is a when it is an ideal instrument. That means no loading effect. That means there is output meter resistance is infinite, but that may not happen in reality. So if the resistance is not infinite, then I ask you to derive this expression E0 by EEX, and hopefully all of you derive this, because all this homework may come to your exam. And then again, if you don't derive in this time, you have to copy during the exam. Okay, and during the viva you cannot do it. So now if you see that this is a nonlinear equation, so the response will be nonlinear, and the nonlinearity increases if the meter resistance is high. Meter resistance is comparatively low. Now let's see that to minimize the effect of nonlinearity, we can add one resistance, another resistance, which is R lin, means linearizing resistance. If it is equivalent to equal to Rm, then the linearizing effect and non-linear effect can be minimized. So you see that in this curve, that if it is Rm is considerable, then Rp by Rm will increase, and the curve deviate more and more from the linear curve, which is Rp by Rm equals to 0. Now you see, if we apply, if we introduce some resistance R lin, which is equal to the Rm, then you see how the linearization is going to happen. So this nonlinear curve will become less nonlinear, as there is a dip in the initially from the linear curve, and there is little bit rise in the later stage with the linear curve. So with R lin, it is much more beneficial, because the curve is less nonlinear. Now after that, power effect, the maximum power which can it withstand, that is described. And you know, if the maximum power which the device can withstand, the input power is more than that, the device will not sustain, it will be damaged. So based on that, you have to choose that how much maximum power. And then we discuss how the maximum power is related to the sensitivity, and then how the sensitivity can be increased with the power rating increases. So we discuss all those things. And then in detail we discuss how the construction could be, and how the wiper is touched, and then how this one full wound resistance is not considered. So resolution, how it is affected, and to get good resolution, what we can do. So all those things we discuss. So strain gauge is over in the last class. Sorry, this potentiometer. Now today we shall start a different sensor, which is very important and popular in real life application, and that is strain gauge. If you have lab, I don't know now you are doing video lab or not. So if you have lab and you are in campus, then this strain gauge, there is a full experiment on the strain gauge, and then we see that how you can measure even a very small strain using the strain gauge and associated electronic circuit. And you have to design all the associated electronic circuit, you have to take reading, and you have to match with the theoretical strain. That is a quite interesting lab. Anyway, fortunately or unfortunately, you are not, I mean, you are not doing the lab. So let's read the theoretical strain gauge. So if you see the strain gauge, that is a very thin device. We'll come to its construction later. Now, as the name says, strain gauge, that means it can measure the strain. Okay, so strain gauge can measure the strain. And now, if I ask to you in Viva that can it measure only the strain? So it is not. Apart from measuring the strain, there are many other things which it could measure. So if you measure the strain, that means basically it is measuring the displacement. So it is a displacement measuring device. So you know, if you can measure the displacement, you can measure the velocity and acceleration as well, because it comes from the displacement. So this is in the chapter of displacement measurement, but it is very popular to strain gauge as it is readily used to measure the strain. Now let's come to a basic principle how strain gauge can measure the strain. Suppose you have a coil, or you have a wire, and that wire may be conductor wire, and that may have some resistance L. Now suppose if you give some strain, what does it mean? You know that what is stress and what is strain. So if you give some stress or strain, what will happen? The length of the wire, either it may change, or the dimension of the wire it may change. So suppose if you have a wire and you apply some force, and then the length of the wire will change. Now if the length of the wire will change, the resistance wire of the wire also will change, because we know that the resistance R will be equals to rho L by A. What is rho? Rho is the resistivity, L is the length, A is the area. So if the length changes, the resistance also will change. Now, if this change of the resistance we can measure by some means, okay, can we tell what is the change in length, dl? So if we know the change in length, we can tell what will be the strain. Okay, so basically the change in length or the displacement is measured by measuring the change in resistance. The change in resistance may not the direct measure. We can have associated electronics with it, that we can discuss later. So what is the basic principle then? It is a kind of resistance strain gauge which is most popular and widely used. So the basic principle is if we apply some strain, the displacement, the length will of the length of the wire will change. If the length of the wire will change, the resistance will change. If we can measure the change in the resistance, we can calculate the change in the length, with which we can calculate the strain. Okay, this is the basic principle. Now, if a strain is applied in the conductor, uh, it might be stretched. That means if suppose I have an wire, I apply some force, or maybe say I apply some force in the down direction and the wire is on vertical. So what will happen? The wire will try to expand or stretch. And now if I have wire or some metal, and then I apply huge force on the top, then what will happen? It may stretch. Okay, so it may compress or the wire may stretch, so its resistance will change accordingly. Why its resistance will change? There are few reasons why its resistance will change. Let's try to discuss it. So when we apply some force, or what will happen, or strain, the change in dimension will occur. Okay, the wire or the material may change with dimension. The change in resistivity may occur, rho, which is here. So dimension of change in dimension may occur, change in resistivity may occur. Okay, and so change in resistivity is not common for all the material, particularly when the material is piezo resistance material. uh, so then the resistivity change will occur. So otherwise, if the resistance is not piezo resistance, if it is a simple wire, metal wire, change in resistivity will be so small that we can neglect it. So now let's see what can occur. So change in dimension can occur, change in resistivity can occur. Now if you derive, so this derivation is not given here. because derivation is available in any book, and if I read the derivation you will get bored. So I consciously excluding the derivation. I am writing this as a homework. So in the slide you see there is a homework there where I write prove that dr by r, that means change in resistance, will be equals to dl by l, change in length, into 1 plus 2 nu. What is that? 1, you know what is 1. And the nu is the Poisson's ratio. What is Poisson's ratio? Poisson's ratio is small d, that means diameter change by capital D, original diameter, and length change delta L by capital L. Again, I am telling, so suppose you have a wire, suppose you have a wire with diameter capital D, and then you are stretching the wire, then the change in diameter may happen delta D, and earlier it might have the L, and due to force applied, the change in L could be delta L. So the Poisson ratio gamma will be delta minus delta D by capital D divided by delta L by capital L. That is called the Poisson ratio gamma. So where so if you see that the resistance change in wire, if you see that the Poisson ratio now it is clear. So the change in resistance dr by r will be equals to dl by l, that means change in length, into 1 plus 2 gamma, which is the Poisson ratio, plus I said that in some material that if you apply some force or keep it deformed, if the material is piezoresistive, so if the material is piezoresistive, then the resistivity will change. Otherwise, if it is material is not piezoresistive, the resistivity will not change. So if the resistivity is changed, that also if we take care, so d rho will be the change in the resistivity. So dr by r will be equals to dl by l into 1 plus 2 gamma plus d rho by rho. So this expression you can see in any book, it is proved. It's a simple algebraic equation. So you have to follow and this will be your homework. Okay. So all the terms I explained in this equation. Now let me see if you have any query. Okay, there is no query. So let's proceed further. So now if you define the gauge factor, what is the gauge factor? Gauge factor will be dr by r divided by dl by l. That means change in resistance with respect to initial resistance divided by change in length with respect to initial length. So the gauge factor dr by r is defined as dl by l. So if we divide it the left hand side with the dl by l, then what we will get? Dr by r divided by dl by l will be equals to 1 plus 2 gamma plus d rho by rho divided by dl by l. So now let's think about all those things. So why 1 is coming? 1 is coming due to change in resistance. So when the length changes, why 2 gamma is coming? Due to the change in resistance when the area changes. Okay, because it is including the Poisson ratio. And why d rho by dl by l coming? This is change in resistance due to piezo resistance effect. So the gauge factor is defined the combination of three terms 1 plus 2 gamma plus d rho by dl by l. So this is a very important formulation. So all of you should prove it. So that's why I gave it as a homework. Okay. Now let's proceed further. So 1 is due to the resistance change due to the change in length. 2 gamma is the resistance change due to the change in area. And d rho by rho divided by dl by l is the basically the resistance change due to piezoresistive effect. What is piezoresistive effect? If we apply some force or pressure on on some material, not all the material will show, then what will happen? Its resistivity changes and its resistance changes. Now, suppose let us consider, so the combining the
whole three terms on the right hand side, we can tell it is a G, which is the gauge factor, capital G. So if the all three terms are capital G, then what is our expression is coming? Let's see if I wrote. Oh, I did not write. So the expression is coming dr by r divided by dl by l, which is our strain. So dr by r divided by epsilon, we can write epsilon equals to dl by l will be equals to g. So dr by r will be equals to epsilon g. So dr, this change in resistance, is proportional to epsilon, which is the strain. So change in resistance will be proportional to the strain. Okay, this is the formulation. So if I come again, so gauge factor is G, which is defined as dr by r by dl by l, and that is a combination of three terms. One, which is coming due to resistance change due to change in length. 2 gamma, which is coming due to resistance change due to change in area. D rho by rho by dl by l, which is coming due to the resistance change due to piezoresistive effect. Now combining these three terms, if we call these three terms are constant, combination of these three is constant, which is called the gauge factor is G. So we can write G will be equals to dr by r by epsilon. Epsilon is the strain. So we can write dr by r equals to epsilon G. We can write dr equals to r epsilon G. So dr, that means change in resistance, is proportional to epsilon, which is the strain. So change in resistance is proportional to the strain. That is the main takeaway from this slide. Now, few more points I want to discuss here. Now, suppose if the material is a simple wire, it may be wire or metal wire, then the piezoresistance effect, that means change in resistance due to the change in application of force or this pressure, that will be effect will be zero. So we can neglect d rho by rho by dl by l equals to 0. So we can neglect it. Then what we are getting? Gauge factor is coming. G will be equals to 1 plus 2 epsilon. Okay. Now, if you see epsilon, no, sorry, 1 plus 2 gamma. Now, if you see gamma, which is the Poisson ratio, and for metal, the Poisson ratio is generally in the range of 0 to 0.5. All of us know it. Poisson ratio of metal is in the range of 0 to 0.5. Now, if we assume a typical Poisson ratio of 0.5 of a metal, a typical meter, then what will be our gauge factor? So G will be equals to 1 plus 2 gamma. So we will see 1 plus 2 into 0.5 equals to 1 plus 1 equals to 2. So in typical metallic strain gauge, okay, when this pure resistance effect comes, then the strain gauge becomes semiconductor strain gauge. I will come into later. So for not semiconductor strain gauge, but a pure metallic strain gauge, the gauge factor normally is near 2. Okay, if you see in the lab, whatever strain gauge we have, gauge factor is 2.2 or 2.02, something like that. So it is near 2. So that means you see that dr by r divided by epsilon will be equals to 2. So based on that, if we know the initial resistance R, and if you know the epsilon, if you know the gauge factor G, the epsilon can be find out very easily, and which is called the strain. So this is the basic philosophy or basic principle of operation of strain gauge. Okay. Now let's see if you have any query. You can ask if you have any query. Okay, last part I will be repeating. It's okay. So whenever you will have some doubt or want to listen once more, just tell me that which part I have to repeat. I will be happy to repeat it. So, so let's see what we are getting. So I said that this expression, which is written as a homework, dr by r will be equals to dl by l into 1 plus 2 gamma plus d rho by rho. So this is the change in r due to application of strain. So now if we divide dr by r divided by dl by l, what we are getting? We are getting 1 plus 2 gamma plus d rho by rho by dl by l. Now if you see, 1 is coming due to the resistance change, due to the change in length. 2 gamma is coming, or nu, whatever you say. So 2 nu or 2 gamma, whatever, is coming due to the resistance change due to change in area. And the last part is coming, the resistance change due to piezoresistance effect. So now if we forget about, because no material shows the piezo resistance effect, forget about the material which is kind of semiconductor which will show the piezo resistance effect. The last term we can cancel out. We can take it as 0. So what is the terms we are getting? 1 plus 2 gamma. And we call it as a G, or the gauge factor. So dr by r divided by epsilon, which is dl by l, which is strain, will be equals to G. So dr by r will be equals to epsilon G. So dr will be equals to r epsilon G. So dr will be proportional to epsilon. So change in resistance will be proportional to strain. Okay. So, so if we apply some strain, the in strain gauge change in resistance will occur. If we can measure the change in resistance, we can easily determine the strain. That is the main philosophy. Now, what I am saying, for a typical metal strain gauge, which is very popular and very stable instrument, the for metal, the nu or gamma, which is a Poisson ratio, is generally 0 to zero point 0.5. So if we assume for a metal the Poisson ratio is 0.5, so 1 plus 2 into 0.5 equals to 2, which will be the gauge factor. So gauge factor of metallic strain gauge is very near to 2. And in lab, whatever, sorry, excuse me, whatever strain gauge we have, that is also gauge factor very near to 2. So metallic strain gauge, the gauge factor is very near to 2. So if we consider this piezo resistance effect, later will come, we'll see how the gauge factor is changing, but please don't bother with it. Now you think about the metallic strain gauge. So in metallic strain gauge, you have a long metal wire which may be differently shaped, and then you apply some strain on it, then the resistance will change, and which will be proportional to the gauge factor, which is 2, which is proportional to the strain, and the multiplication factor will be the gauge factor, which is 2. Okay. So with that, we will proceed. So now tell me if you understood this. So I repeat it. So now can I proceed, or you have anything or any query or anything you want to proceed? Okay, fine. So let's proceed. So if you ask question, if you interact, then it will be it will be a very good class, and there will be some meaning of teaching. Otherwise, see, from my perspective, I am teaching a computer screen, which is very painful actually. Now, if you see that what are the different types of strain gauge that you generally see, so there are 7 different types of strain gauge. So among them, I should say that 5 is okay. So let's think about the first, unbonded metal wire strain gauge. I'll come what it means. Now come to second, which is bonded metal wire gauge. This is also important. Then come to 3, which is bonded metal foil gauge. That is also very important. 4, 5 is not that important because this is a kind of construction in detail. So if we forget about 4 and 5, then again 6, sorry, if we think about the 4 and 5, you will see that vacuum deposited thin metal film gauge and sputter deposited thin metal film gauge. So this is a kind of construction. The main takeaway is the thin film gauge or thin metal film gauge. That is, so we combine 4 and 5 in a single category, which is thin metal film gauge. Forget about that how this thin metal film is produced. And then if you see that 6 and 7, the last term is semiconductor strain gauge. So we concentrate on the semiconductor strain gauge, apart from forgetting that bonded or diffuse. Okay, so basically, if we say that 5 important types of strain gauge are there: unbonded metal wire, bonded metal wire, bonded metal foil, thin film gauge, and semiconductor gauge. So we'll try to discuss it. Okay. So another thing I want to repeat that in this discussion, mainly I said that strain gauge is measured for strain measure used for strain measurement, but as a byproduct of strain, basically it is measuring the displacement. So as a byproduct of strain, it can measure the force, it can measure the displacement. If it measures displacement, it can measure the velocity, and it can measure the pressure and all other. These are the other parameters which you can measure with the help of strain gauge apart from measuring strain. Okay, let's go to the next one. So this is first type of thing, unbonded metal strain gauge. Okay, now try to see the construction. Okay, so this is very important construction. So if you see that there are this unbonded metal wire, basically there are two tables. You see there is a fixed base, like this, and there is a plate on the fixed base which can move with the input motion. You see input motion is given. Okay, and there are four wires, one, two, three, four. There are four wires. So the unbonded metal wire gauge employs a set of four wire, or we can say that set of four resistance, and I can say it is a preloaded resistance connected in a Wheatstone bridge. So what does it mean? Again, I am coming. Why it is a preloaded resistance? Because so the wires 1, 2, 3, 4, they are the metal wires. They have some resistance. They have the resistance, and the resistance will change based on the tension of the wire. So now if you see that the preloaded resistance, that means these four wires are in a specific tension, and that is called the preloaded resistance wire connected in a Wheatstone bridge. So these four wires are connected in a Wheatstone bridge, which is shown in the right hand side. So you see these four wires are the four arms of the Wheatstone bridge, which is R1, R2, R3, and R4. And there will be internal battery, and you will get the output from the Wheatstone bridge. So I am telling again. So this unbonded metal wire gauge, it has a two tables. One is fixed, and another table can take the input motion. So if you see when there is an input motion, the two wires will be relaxed little bit. Two wires tension will increase, and these four wires forms a wire connected in a Wheatstone bridge, as shown in the right hand side diagram of the right side. So initially, the strain and the resistance of the four wires are normally equal. So initially, generally what we do, this resistance of the four wires are normally equal. And so in such a cases, the Wheatstone bridge will be at the balance condition, because resistance, these four identical wires, and it is get tense such a way the resistance are equal. So initially the strain and the resistance of the four wires are normally equal, which gives the Wheatstone bridge a balance condition. That means E0 equals to 0. Now suppose that we gave some input motion. So when we gave the input motion, you see that it increases the tension of the two wires and decreases the tension of other two. For example, you see that 1 and 3, they are both connected in the same way, and 4 and 2, 2 and 4 are connected in the same way. Now suppose if we give some input motion, okay, what will happen? The input flexor plate will go, let's say, outward. So if it goes outward, so tension in the 1 and 3 will increase, and tension in the 4 and 2 will be relaxed. Okay. So when we do so, the tension in the two wires will increase, and this tension in other two wires will decrease. So you should mind it that none of the four wires will go slack. That means uh, zero tension, it falls on its own weight. No, only tension will increase or tension will decrease, but all the four wires will remain tight. Okay, no wires will be slack. No wires will be slack. So if the tension is increased, so and if one other set of wires is relaxed, so what it causes? It causes the corresponding changes in resistance. So when the resistance change will occur, what will happen? The Wheatstone bridge will become unbalanced. Okay. When the Wheatstone bridge will become unbalanced, you measure the output voltage with the help of a very good potentiometer, very good voltmeter, and the output voltage will be proportional to the input motion. Okay. So if we see that the resistance arm is chosen such a way that R is generally 120 ohm, and you know that the strain gauge constant G will be equals to generally 2. Generally, the voltage applied is 5 to 10 volt, and the output voltage we get is very small, which is kind of 20 to 50 millivolt. And by measuring the output voltage, you can calculate the change in resistance, and from there you know the gauge factor, you can calculate the strain. So this is the basic principle of unbonded metal wire strain gauge. Okay, unbonded means it's connected with the hook of the two plates, it's not bonded with the plate. Okay, so if there is any query, tell me. If you want to hear it again, or if you have any query, you just tell me or write it, whatever is good for you. So I will be happy to explain. Okay. So then let's try to go to the next type, which is the most popular. Uh, sorry, before metal foil. This is the. Sorry, somebody is asking something. Let me see. No. Okay, fine. So okay. So this is the kind of bonded, uh, unbonded metal wire. Then the next type will come, which we call as the bonded metal wire. Okay. So the bonded metal wire is now today's this first type what I discussed, unbonded metal wire strain gauge, is not generally used. Very less used. Mostly what we use it is a bonded metal wire or the bonded metal foil. So now let's see what is bonded metal wire. So today the bonded metal wire gauge is largely used, and it has largely replaced the unbonded metal wire. And also you will see the next section that bonded metal foil also will be largely used. Okay, so now in this case bonded metal wire, what we do, a grid of fine wire is connected to the specimen surface where the strain is to be measured. So here you see that the only single wire is connected with the help of two hinge, but in bonded metal wire, a grid of, that means this wire can be many wires, a grid of wires connected not through the hinge, but it is bonded with the surface where we want to measure. That means it is fixed by means of paste, glue, or something. Okay. So the main difference is instead of single wire, we have a grid of fine wires which is connected to the specimen surface. That means it is where the strain is to be measured, as it is cemented to the specimen. That means it is pasted on the specimen surface. So when the tension on the specimen appears, the wires also get tensed because it is fixed on the surface. When the compression comes, the wires get compressed. When the elongation comes on the surface, the wires get elongated. Since the material and the wire are pasted very firmly together. Okay. So it is a kind of unbonded type, the same result. Then these four wires are connected, which is connected on the specimen. The terminal of the wires are connected in the Wheatstone bridge. We excite the Wheatstone bridge with some voltage, and then we observe the output. When there is no strain, when the output will be zero, because four wires will be equally strained or equal resistance. When there is some strain applied to the specimen, the resistance change. Due to that, the Wheatstone bridge gets unbalanced and you get some voltage output, and that voltage output can be converted with the change in resistance and ultimately the amount of strain which is applied to the surface. So in lab what we do, it's typically same experiment we set up. It also has the Wheatstone bridge and all the arm resistance of the Wheatstone bridge we know. And there is a very small surface, few inches, 3, 4, where we can apply the strain by pushing the surface. And when this strain appears, then the Wheatstone bridge becomes unbalanced. Then you people will measure the voltage and you know all the resistance of the Wheatstone bridge. With the help of these things, you calculate the output versus the input change in resistance and ultimately the change in state. And with that, what you do, you measure the displacement of this surface where the strain gauge is pasted, and you calculate theoretically what is the value of strain, and you see that there is very small amount of strain produced in that surface because it is a very small lab experiment, and you see that order of that is matching whatever you measure from the voltage and convert it to strain. Okay, that is a very beautiful experiment. I don't know when you will come and do it, but it gives everything about the strain gauge. Okay, now tell me any query. Okay, so there is no query. um, let's proceed then. Next, what is come, that is the metal foil. It is the similar principle of the wire, bonded wire, but instead of wire, see here it is one thing is very clear. If you use one single wire, the resistance is less, and this change in resistance is less, and its sensitivity will be less. So you need basically the many wires uh, to be owned in a surface. So you can do it if you have a physical wire, its thickness is a little bit more, so number of wire in a surface will be less. So what you can do a bonded metal foil. So today this type of thing, you will see a thin film metal foil, just a film type of thing, and you will see very thin wires are wound like this. You see this very thin wires are wound like this. Okay, see, you see these are the thin wires. Okay, these wires is coming and bending and coming again, bending again, coming again, bending again, like this. Okay, and so many small wires, and it's called a metal foil. So mostly these type of things are used today. So the sensing elements are formed from the sheets of very thin wires, even so thin that 5 micrometer thick. Okay, so it is done, it is not actually the wire, it is done by the photo etching process. Okay, so you cannot take so thin wire and bend it to make such thing, so it is done with the etching process. Etching process means you have some gating and all, and you etch that with that material of the wire, and then somewhere you will get the wire etched, somewhere you don't have anything. And so what is the advantage? Advantage is that it gives you very flexible thing. So nowadays this metal film, you will get just kind of a sellotape, so thin film, and then you take this kind of a sellotape, which is basically a strain gauge, and put a glue on it and paste it on the surface. That is what you have to do. So it allows a great flexibility, and in stress analysis, the goal is to measure the stress at different geometrical point. That will come. This geometrical point is very important. Before that, just before coming to geometrical point, so at some point you need to know the stress. So in that point, you just bring this metal foil, put a glue on it, and paste it firmly so that it moves with the stress of the surface as the surface elongated or contract. And then you connect these two ends in the Wheatstone bridge. You arrange the Wheatstone bridge, you give the meter, and then ultimately you measure the strain. So this is the same principle as the bonded metal wire, but the construction wise it is more flexible and more convenient to use it. And at some geometrical point, you go and fix it. Okay, and you know that the strain produced is proportional to the output voltage, and you measure the output voltage, multiply it with some factor, and you know what the strain is. Okay. Now you might be asking, you might be thinking a few questions which are very good to discuss here. So you are thinking that when you say that, what is the scope? Yes. Any query, please. If anybody is asking anything, Okay, fine. Maybe by mistake a microphone gets switched on. Okay, so now let's discuss a few aspects which is very important to discuss. So whenever you say a strain at some point on the surface, there are few things come into your mind. First thing is that at what point. So it is a pinpointed thing. First thing, but when you use whatever the metal foil, which is even very less, few inches long, but still it will not give the pointed place where the strain is. It can say that in this small amount of surface area, this strain is acting like this. This is the one point come into play, come into in your mind, the query. The second thing, whenever you see the strain, the direction is important. So still now, whatever the things I discussed, I did not say anything about the direction. Okay. So these 2 points are very, very important to consider. Maybe next class I'll consider these 2 points are very important. Particularly, this direction is very important to consider because the single strain, as you know, that if it is a surface, the direction will be two directional x y. If it is a cube, it might be x y z, and the cross directional also. Okay, so that means a single strain gauge cannot make it. This is the first point. So we need to have different structure. So maybe as now the time is over, tomorrow we can do it. Tomorrow from 9 to 10 again we'll discuss it, and then we'll proceed. So in the mean point, you keep on reading the Doebling and try to solve the uh, question answer and the problem from the Doebling. Okay. So now you tell me if you have any query in today's class or even in earlier class. Anybody has any query? None of you have any query? Okay, then if you don't have any query, then we can stop here, and tomorrow we can discuss again. So thank you all of you for coming to this class, and uh, we'll meet tomorrow again, and hope that many more students will come, not only 30, 40 students. Okay. So thank you all of you. Have a good day. You have more classes today, so you try to attend them. It's fine. So thank you. Let's dismiss the class.